right, welcome back, and we're continuing talking about longitudinal waves, and now we want to be specific. We've got an example of what longitudinal waves are. Sound waves. Sound waves are longitudinal waves. Okay, so if we want to give an example of longitudinal waves, we can talk of sound waves. If you want to give an example of transverse waves, which one will, quickly come to mind? Sea waves, okay, or water waves. If you drop something onto a pond of water, you see those ripples forming. That is an example of a transverse wave. But for sound, the type of waves we're talking about is longitudinal waves, okay? Sound waves comply with the general wave equation. What is the general wave equation? Okay, the general wave equation, we know that speed equals f times lambda, frequency times the wavelength. Or we know that speed generally is the distance covered by a moving wave divided by the time it takes to cover that distance. All right. So it actually obeys that we can use it to solve wave problems based on sound. We can use this wave equation here. Next, now sound moves in a medium. That's what we need. Or waves move in medium. Okay, like sound will move in air. Air becomes the medium in which sound waves move. Okay, now if we're talking about ocean currents and waves, you are at the beach there and watching the waves coming to the shore. The wave is moving, and what is the medium in which it's moving? It is the water. The water is the medium. So sound waves will also move in different medias, okay? In different media. And let's see what the speed of sound is going to be like in this different media. Right. First, looking at air, and this time, let's say this is refrigerated air in some way at 0 degrees Celsius. Sound will move at 331 meters per second. This is given in meters per second. That's how fast it will move in cold air. Generally, out there, it will move at 343 meters per second. Sometimes this is, you would see when we deal with Doppler effect calculations, that they would normally say, take your speed of sound in air to be 340 meters per second. But we have these constants that are more or less the exact speed of how the sound waves is going to travel in a media. If we isolate hydrogen gas and we allow sound to pass through it, it will move at that very fast speed. Okay, so if we want things to happen quicker in terms of transporting sound, we will need to create a hydrogen tube somewhere, a tube filled up with hydrogen, and allow sound to go through there. In water, that's how fast sound moves in water. So you can see in water, we should be able to hear sound much quicker. Okay, aquatic animals would hear sound much quicker. Sea water, 1,560. So this is ordinary water, but at sea water, look at how fast sound travel, 1,560 meters per second. If we're talking iron and steel, that's how much fast it moves. Glass, that's how much fast it moves. Aluminium, it moves at about 5,100 meters per second. Right, now let's come to how these sound waves behave. Now, sound waves, just like light waves, they also undergo what we call reflection, okay? So they undergo reflection. How do we know that this reflection is happening with sound waves? When we hear echoes from distant buildings and inside caves. Have you ever encountered a situation where somebody is chopping something, maybe trying to cut a piece of wood at a distance where you've got these huge buildings around, you would always hear the echo of the axe hitting the wood. Okay, now that echo tells us that these sound waves, when they travel in air, they hit those big buildings and they are reflected back to where they are coming from. So the echoes tell us that sound waves can or are reflected. Okay, when these sound waves hit obstacles like these big buildings we're talking about, these waves actually split up into three parts. Okay, they split up into three parts. One, part of these waves or part of the sound wave is transmitted. What does transmitted mean? It means it is allowed to pass through that obstacle. Two, part of the sound waves are absorbed into that obstacle. So part of the noise, the sound that comes from whoever is cutting that wood that I gave an example of, is absorbed by that wall. Little of that sound goes back, not the whole sound wave goes back. That's why the echo is not as intense as the real sound. Okay, and lastly, part of this is reflected. Okay, so part of the sound wave is reflected, which gives us the echoes. All right. Next, going on talking about how these sound waves behave, they also undergo refraction. And what is refraction? The change in direction of a wave as it moves from one medium to another, and of course with a different optical density or different density. Say sound is coming from air. Okay, there is sound wave coming from air, and then it enters a pool of water. When this sound enters there, it's going to change direction, and changing direction, so instead of continuing in that direction, it may change to go down there. As it goes down there, this is a pool of water. It has been refracted, and it is refracted because it has changed the speed at which it was traveling. Okay, thus the speed of sound, of the sound wave changes as it depends on the type of medium in which it's moving. From air to water, it has to change. Okay, person here sound better on a cool day than in a hot day. Why? Because sound travels slower in a cool weather than in a hot weather. Okay, the issue of resonance there. This is when object made to vibrate at its natural frequency by another object vibrating at the same frequency. All right, see you in the next section.